on the phase diagram, you can have any state of matter. So there's information here. I'm not going to read it to you, but it's some information here about waves and how waves travel. To take all of this and summarize it very quickly, what it's basically saying is that waves are a phenomena that can occur. When we have a wave, it's an occurrence that takes place in the universe, and it transfers energy. Mechanical waves are going to use matter to travel. So think of this like an ocean wave, or if you throw a rock in a pond, you can kind of see the water coming out from the center and those little waves as they travel outward. It's important to understand that it's not the matter that's traveling. The matter is just being used as a conduit for the energy to move. So mechanical waves are going to need matter. Electromagnetic waves are going to be able to travel without matter. So light is an electromagnetic wave. It can travel through matter, but it doesn't have to. And that's how the light from the sun can reach our earth, is because it's traveling without that. Sound waves, on the other hand, are mechanical waves. Sound waves cannot travel without some kind of matter. Sound waves travel at the highest velocity in a solid, but the lowest velocity in a gas. We have a hard time remembering that because most of the time when we hear sound, we are hearing someone speak to us, and we're hearing that sound take place over the airwaves. Or I'm sorry, not over the airwaves, but over air itself. Sometimes we refer to airwaves, that's our name we use for radio waves, which are actually an electromagnetic wave. But just understand that a wave is a movement of energy from one place to another. And remember that electromagnetic waves do not require a medium. That's the matter that's used. But mechanical waves do require a medium. And by medium, I mean matter. All right. This slide talks about the three most common types of disturbances that waves can encounter: reflection, refraction, and diffraction. So they sound similar. Let's talk about what they are. Reflection you're very familiar with. It's when a wave hits something and it bounces off. All right, so this is what happens when you look in the mirror. Light bounces off. And usually, it's going to follow the law of reflection, unless you have a rough surface, in which case it's called diffuse reflection. Refraction, this happens when it goes from one kind of medium into another. So if you put a pencil in a glass of water and you look at it, it might not line up, and that's because it travels at different speeds through the air and through the water. Now diffraction is a little more complex. This is where the wave is also going to bend like it does in refraction, but that's because it hits a barrier or an opening of some type. You can remember that because the letter D here, think about a door. If that door is open, it can diffract through the door. So a barrier or some kind of an opening is going to cause diffraction. Refraction is going to happen when you have different materials that's passing through, so different mediums. And then we also have other kinds of interference, which we can call constructive and destructive. So constructive interference is when you have two waves that kind of meet and it forms a bigger wave. Destructive interference happens when the crest of one wave hits the trough of another and it results in a smaller wave. So if the amplitude of the wave is increased, it's constructive. You're constructing the amplitude. And if the amplitude is lower, it's destructive. So what are you destroying? You're destroying the amplitude. So think about it in those terms, and that might help you. Also related to motion in some ways, but not directly, we have work. And what you think of work and what physics considers to be work are two different things. So here it says work is a transfer of energy when applied force moves an object over a distance. For work to be done, a force must be applied in the same direction as the movement of the object, and the object must move a certain distance. So let's just kind of take a moment to take that apart and analyze it. So what it's saying here is that we have to have a force applied, an object has to move, and an object has to move in the same direction as a force. The formula we use for that is W equals FD. This is work equals force times distance. Remember that work is measured in joules because it's talking about energy, and all energy is measured in joules. Force is always measured in newtons. And distance is going to be measured in meters. We also have some mention here of the simple machines. Machines, essentially, these make work easier because they will multiply your forces or they'll multiply your distance. Now understand there's a trade-off here when you use these machines. If the machine is going to increase your force, it's going to decrease your distance. If I have a machine like a broom is not going to increase my forces. What a broom does, and the reason that a broom is so effective, is that a broom will increase the distance over which my force is spread, but my actual forces I'm applying, that is reduced by the same factor. So you have a trade-off. If you multiply one of these, going back a little bit, if you multiply your force times 2, you're dividing your distance by 2. If you're multiplying your distance times 5, you're dividing your forces by 5. So there is a trade-off, something you have to give up in order to get the benefit of the machine. Now here it talks about effort force, resistance force, so we abbreviate that FE, and F with the subscript of R. We have effort distance and resistance distance. Now what this means is the effort is going to be what you put into the machine, and the resistance is going to be what comes out of the machine. Alright? So here's an illustration of a lever that's being used to pry open a can of paint. It says your mechanical advantage is going to be the number of times the machine is going to multiply your force. And the way we find that formula is we have the resistance over the effort. So this is the output over the input. In some situations, if you were looking at how the distance is calculated, you could have the distance output over the distance input. And so like in the broom, where you're not really getting a benefit to your force, what you're getting is a benefit to your distance, you would use this formula. And again, these formulas are going to be given to you on the exam, so you don't have to memorize all of those. Here, this slide talks about radiation. It says we have alpha, beta, and gamma, and it talks about half-lives. And the way we solve this, the way we look at this, remember that an alpha particle is going to be two protons and 2 neutrons. It resembles the nucleus of a helium atom, and is the largest of these radioactive particles that are shed when something goes through decay. A beta particle is going to be an electron in most cases, or it could be a positron. It's a very tiny particle. Now, alpha can do the most damage in some situations, but it's the easiest to block yourself against. So an alpha particle cannot penetrate a sheet of paper. To block a beta particle, you need a thin sheet of foil, like maybe some aluminum foil. Gamma can be a lot more serious, and it can penetrate most materials, but you might be able to block it with maybe a cubic foot of brick or stone. That can slow it down. So the thing to remember is that when something goes through alpha decay or beta decay, it might also have gamma decay in addition to one of these two. You will never encounter gamma by itself. It'll always be with one of these two. Looking at half-life, you can kind of connect that to specific heat capacity. And that's a number that's special to each material. The same thing is true with elements and their half-lives, because every isotope is going to have its own half-life that's special to it. This says that radon has a half-life of 3.8 days. Some materials have half-lives of thousands of years. So again, that number is very special to that one material. So every half-life is going to result in half of the material being taken away to where it's no longer radioactive. So if you have, let's say you have 10 kilograms of a substance, of a radioactive substance, and it has a half-life of 1 day. After 1 day, only 5 kilograms is still radioactive. After 2 days, only 2.5, and so forth. So every half day, you're basically dividing by 2 to get rid of that. It's a number of times you would multiply by 1/2. So 3 half days, you're going to multiply by 1/2, 1/2, 1/2 to find out how much you're going to have left. It's still going to be radioactive. This talks about fission and fusion. Remember that fusion is where things break apart. I'm sorry, that's not true. Fusion is where they come together. It says fusion is the energy source. You're going to get some energy like you would here, not as much. So most of our energy comes from fission. And the way you can remember fission is sometimes if we see a rock that has a crack in it, we call that a fissure. And that's just kind of like a break in that rock. So we're breaking this atom open, we're breaking it apart. And as we do that, what's happening is tremendous amounts of energy are being released. We don't have the same pollution that we would have when we generate electricity from nuclear fission. We do have nuclear radioactive waste we have to deal with, which can be kind of a conundrum to figure out what to do with in some situations. Fusion, when this happens, we are fusing things together, all right? And what happens here is we basically have small, tiny atoms that are being stuck together. In many situations, it's like hydrogen. And as they are being stuck together and they collide, they combine to form larger nuclei. And if you think about it, say you have 6 hydrogen atoms. If you can somehow stick all those together, then basically what you have formed is carbon. So in both of these situations, what you have going on is you have atoms becoming atoms of different elements. So you always have a different element when this occurs. We get most of our nuclear energy, we get all of it from fission, none of it from fusion. We don't have the technology to really get a lot of it out of fusion. So we're going to do one question, then we're going to stop for the day. Here it says the specific heat of pure water is 4.184 joules per gram times degrees Celsius. Before I go on here, I just want to throw this out. If I had kilograms here for my unit instead of grams, then I would have a comma there because there's 1,000 grams in a kilogram. It says a 10-gram sample of pure water goes from 22 degrees Celsius to 32 degrees Celsius. Take a moment, go ahead and try to solve this. Remember, you're trying to solve for a Q. How much energy or how much heat did it gain? So heat is a movement of thermal energy. See if you can figure that out. Take a moment to do that, and then we'll go over the answer together. All right, so let's look at this. So when I'm solving problems like this, I always like to start by writing my formula down. And then I will just replace the variables with the actual numbers. So we're trying to find Q. We know that we have a 10-gram sample. We know the specific heat capacity of water is going to be and we also know that our change in temperature, if it goes from 22 to 32, that means it's a positive 10 degrees Celsius. All right. I like to write the little positive symbol there just so I remember that it's not being taken away, and that way I won't mess up. All right, so what I'm basically doing here is I'm multiplying 10 by 4.184 times 10 again. 10 times 10 is 100, so that's like moving the decimal place over 2 times. So my energy is 418.4 joules. Now this one was actually quite easy because I'm multiplying by multiples of 10 here. So my answer choice for this one is B. So that's just some of the presentation to review for the EOC. Feel free to watch the video as often as you would like. Please bring me specific questions for things you do not understand or things that you are confused on so that we can address those. And we will continue with another video following this one that will continue to go over the same structure for the EOC and examine other aspects of our science curriculum. Thank you for watching.